Okay, recall when we got to the surface integrals previously, we developed all this. We have the example of x equals b cosine u, y equals b sine u, which gives us a circle of radius b as u goes from 0 to 2 pi. So circle of radius b. Then we could have z equals 2v and we get a cone. Sides have slope 2. You can see how that works out. We're going to see that because we're going to actually do an integral over this. Okay, last time we stopped here just because of time and other factors. So we're going to go a little further. We could do a parabola where your z is square root of plus of a minus b squared. And that gives you hemisphere radius square root of a. I should have said a squared minus b squared. See what else is going on. Ru and Rv are your u and v derivatives of this function. So Ru, for example, well, actually, I'm working out on the specific example. I don't have a specific example yet. But Ru would be the u derivative of x times I plus the u derivative of y times j plus the u derivative of z times k. And Rv, well, the derivatives, partials with respect to v, same thing. Your text calls these Tu and Tv. Now, this is a quick review of what we already did in some detail. Ru and Rv turn out to be tangent to the surface at a given point. For given uv, you get a point x, y, z. Okay, and these derivatives are going to be tangent, and they're not generally going to be parallel. If they are parallel, it means you have a surface you really can't integrate over, and you have to give them some tricks that we don't worry about in this course. Okay, then if you have a delta u and a delta v, you'll have an Ru delta u vector and an Rv delta v vector that are tangent to the surface. Their cross product will be normal to the surface. So Ru delta u cross Rv delta v should be normal to the surface, and the magnitude of Ru cross Rv. We know, or we learned very early in the course, that if you have a parallelogram defined by two vectors, the area of the parallelogram is the cross product, the magnitude of the cross product of those two vectors. I also mentioned the triple product. Okay, and you should understand, the area or the volume of the parallel like that. One vector, third vector dotted is the cross product of the first two. And you should recognize that at this point, but if not, you should review it. Okay, so magnitude of Ru cross Rv is the area of your surface increment. So your surface increment, delta Sij, and I just used delta Si previously. They said, okay, we got a bunch of surface increments, we just add them up. I'm going to be a little more specific in this development. I'm going to call it delta Sij because of the way we're going to partition our parameter spaces. Instead of a UIVI, we now have a UIVJ. Okay, so we have our, and there's our RU and our RV. Have the given parameters U, I, and VJ. Okay, and then that's times your delta U, I, delta VJ, and we'll make that all explicit in the example. So that your total surface is going to be the sum of these, and that's going to approach this double integral with respect to U with respect to V. We'll fill this in for the example of this cone. And that's also could be written as Tu cross TV magnitude of, because your book uses Tu and TV, but it's just the U and V derivatives of your R vector. There's no real reason to call it this, except that we want to emphasize that these are tangent. And so it's not a bad idea to use the Tu and TV. But Ru and Rv are already tangent. So it's not absolutely necessary. Okay, the flux phi of F through surface. Well, the flux through the Ij element of the surface is the field, the dot product of the field with the normal vector times delta S. Okay, and the delta Sij is just, well, it's this times this. Okay. The M delta Sij, I'll do this, is M times delta Sij is the Ru cross the Rv evaluated at your sample point, Ui star Vj star. And I haven't mentioned the sample point, but we'll see that as we go through. And I do this expression then in terms of a sample point within the delta U by delta V, the I and J U and V intervals. Define a rectangle in parameter space. This is the area in real space of that surface increment. And if we do the Ru cross Rv without the magnitude, we actually get the same magnitude, but we get not only that, but a vector normal to the surface. So that's your normal vector times delta Sij. For the normal vector is a unit normal, and the delta, actually it's not a unit. There it is. Okay, so there's your N delta Sij. We dot that with your F, and we get the flux through the surface. Okay. Now, if that's all written out in terms of these symbols, and this all got smudged, I don't know if it's as clear as possible, but it's pretty clear what we have. If F equals, and I never really wrote this out, so we'll just say F equals a little f times the I vector plus a little g times the k vector plus a little h times the k vector. Now in the original, I looked around for an alternative to this notation, and I can't think of a good one. The problem with F is sometimes your field is the gradient of an F function. You've got to understand that this is not the F function, that F might be the gradient of. So I didn't want to use FGH, but if I use GHK, then K invokes the unit vector in the Z direction if you're not careful. And you go down the alphabet, and pretty soon you get into symbols we typically use for parameters. So we're going to use FGH for the I, J, and K functions or components of F. Now, this is really, instead of just F, it's F of UV. It's actually like a little f of x of u, y of x of uv, y of uv, z of uv. And that is ultimately, if you plug in the expressions for u and v, like our expressions for u and v. Sorry, if our x is v cosine u, y is v sine u, and z is 2v, as it will be in the example we do, then you plug those expressions in here, and now you got f, fill f as a function of u and v. And the same for g and h. So if I write this out just kind of as a recipe, I'm going to have to write out that the flux is the f function, which is now little fi plus little gj plus little hk, where f, g, and h are functions of u and v. And the ij component of the flux is that field evaluated at the point, the sample point, ui star, vj star, in parameter space. Okay, we dot that with the vectors ru, delta u, and the cross product of the vectors ru, delta u, and rv, delta v. Well, r is your x, I plus y, j plus z, k. So the u component is x u I plus y u j plus z u k. Partials with respect to u, where x is your function of u and v, X, Y, and Z are functions of U and V evaluated at your sample point UI star VJ star. Okay, so that's all these symbols mean. And again, we're going to see how that works out. And then you cross that with the V derivative, the RV, okay, the partial with respect to V. So this could be, this is your RU, your partial of R with respect to U. This is your partial of R with respect to V, evaluated at your sample point within the IJ interval. And the sample point within your parameter space is the IJ interval. Well, this cross product again gives you the vector normal, and its magnitude is the area of the region in real space that corresponds to the rectangular region in parameter space. It's a lot to get your head around and sort out, but if you do, then you get a much better understanding of what integrals are, how they're developed, and the specifics of these very, very important integrals, very important for engineering, and of course for physics. But since most people that take this course are looking at engineering, specify engineering, hydrodynamics, electromagnetism, thermodynamics. It's all based on multivariable calculus. It's all notated in multivariable calculus. Okay, well, let's get to the actual example. Now, I didn't exactly stumble through the explanations, but it was late in the day and on the last day of classes, and I was not as conscious as I'd like to be. And I was on top of what I'm saying. So I think I said most of it right. But there's a mistake in there, and there might still be, because as I go through this again, if I don't identify the mistake, I'll point out where I think it is. I've not been able to trace it down. Just something careless, a minus sign where I should have a plus sign. I'm really sure that I should have a plus sign. I'll explain why. Okay, well, anyhow, here's your example. You parameterize a surface by x equals v cosine u, y equals v sine u, where u goes from 0 to 2 pi. This gives you a circle in the xy plane of radius v. Then z equals 2v. Well, that's easy enough. We're going to let v go from 0 to 3. So we have circles of radius from 0 to 3 in the xy plane. And above those circles, we have the various circles that make up the surface. Okay, so above surface of radius v, go up 2v units. So v is 2, let's say. We have a circle of radius 2 down here in the xy plane, we go up 2 units. If v is 3, then we have a circle of radius 3, and z equals 2v. So we're going to go up 6 units. Did I say that right? If v is 2, we're going to go up 4 units. I think I might have said 2 units. So radius is v, we go up 2v, which is 4 units. Radius is 3, we got a bigger circle, so radius is 3, and we got to go up 6 units. We do that for every possible circle, and we get a cone. And it should be obvious why. You can do slices of this thing and so forth, all the things you learn to do with quadratic surfaces and surfaces in general. And you can verify yourself that this is a cone. In any coordinate plane, the sides of the cone have slopes of magnitude 2, because v is the radius of a circle, it's how far you are from the origin out here, and 2v is how far you go up. So you've got v here and 2v here. Your slope is rise divided by run, which is 2. Well, make sure you understand that, because that's one of the easier things to understand. And though there doesn't have to be 2v, if we wanted to do a paraboloid, we could do 2v squared, for example, some quadratic function of v. Well, now, what we want to do is, first of all, get the surface area. Just going to use what we saw more theoretically in the general notation. So first of all, our parameters, u goes from 0 to 2 pi, z goes from 0, v goes from 0 to 3. that's a rectangle in parameter space. So I've maybe labeled this. This is parameter space. A typical increment, a UI by Vj, delta UI by delta Vj increment here, to a sample point UI star Vj star, then maps onto the surface. Okay, we take UI star and Vj star and we plug those numbers in, whatever those numbers happen to be, and it tells us X, Y, and Z, which is a point on the surface, which is the coordinates of a point on the surface. And then this rectangle, all the points on this rectangle, map to some parallelogram, some approximate parallelogram on the surface. Now the surface is curved, so it's not an exact parallelogram, but if your delta X or delta U and delta V are small enough, then it's very close to a parallelogram, just like we're on the surface of the Earth, but this is a rectangular room and we don't see any reason it should curve. We know it should curve. It really probably doesn't. Make sure it doesn't curve because it's a close enough approximation to the shape of the Earth at this point, or the shape into which we've bulldozed the Earth at this point, that it seems flat. Well, this will seem flat, so it's going to seem like a parallelogram as your delta U's and delta V's approach zero. Excuse me, I'm talking too much. Okay. So in notation, here's our X, Y, Z point, and we have this area. Okay, the X, Y, Z point is just X of UI star Vj star and Y of UI star Vj star and so forth, just like it was over here. Move this over a little bit so we kind of see most of this in here. Okay, and the X, the Y, and the Z just are obtained by plugging the UI star and Vj star into these three parametric equations. Okay. The area, as we've argued, is the area of the parallelogram defined by RU and RV, where RU is, well, I'm sorry, the area defined by RU delta UI and RV delta Vj. RU and RV again evaluated at the sample point. And I haven't drawn that out. But I've indicated it here. Okay. RU at the sample point times delta UI is a vector out here in three-dimensional space. RV times delta Vj is also in three-dimensional space. So those vectors span this parallelogram. Maybe it would be just a little clearer, it isn't already, if I just draw my RU and my RV, at least schematically. They're going to have a cross product that's normal to this surface. The area of that little rectangle is going to be this, and its direction is going to be the direction of the cross product. The normal direction will be the direction of this cross product. The area increment then is just what I wrote here: RU cross RV, delta UI, delta Vj, where these RU and RV, again, I keep repeating it, evaluated at the sample point in parameter space. Your N delta S is this, and that pretty much just mimics what I said over here. Okay, so I'm not going to repeat it. But now we say, okay, RU is XUI plus YUJ plus ZUK. And now we're going to actually fill in what we get from the parametric equations. So that is XU is, well, the U derivative of X is negative V sine theta, or sine U. Okay, so that's your XU, so that's negative V sine U, and that's times the line vector. And then yu is derivative of b sine u, okay, which is just b cosine u, and that's times the j vector. And then zu times k, and z doesn't depend on u, z is constant with respect to u, so that's 0, so we don't even have a k vector. So there it is, just an I and a j component that are obtained in a very straightforward manner from these parameters. These parametric equations. Okay. RV is calculated very similarly. It's XV and YV and ZV. XV, you're just going to have cosine U. YV, you're just going to have sine U. And ZV, you're just going to have 2. So you get cosine U times I plus sine U times J plus 2K. Okay, then the area increment is just, again, the magnitude of this cross product, which is the area of the parallelogram that you get here, here, okay, times your delta U and your delta V, delta UI, delta VJ. Again, everything evaluated for your sample point. So the IJ area, the sum of your IJ areas, then the sum of all these approaches this interval in a very straightforward manner. U is going to be partitioned. No, we didn't write out a partition, but we partition U and we partition V in order to get this rectangle in parameter space. So we're integrating over parameter space. We're integrating U from 0 to 2 pi. We're integrating V from 0 to 3. It's a nice rectangle. So the limits on V don't depend on U. The limits on U don't depend on V. Again, that's one and the other, but okay. So there's our integral. We just integrate U from 0 to 2 pi. We integrate V from 0 to 3. And we get the total area of the surface. Now, I should have used more standard notation, something kind of switch notations here. My A's. Generally, we're going to use capital S for surface area. So S, which is the total surface area, I don't need to write a subscript total on there, but I'll do it just for clarity. Total surface area is the sum of all the IJ, all the IJ surface area increments. And that approaches this limit in a way that should be very clear to you from what we've done. Okay. So that's pretty straightforward if you understand this stuff, which is not all that straightforward. But once you understand this, or if you just treat it as a formula, which I don't recommend, I think you're better off understanding it. You're more likely to get the formula right, among other things. But one way or another, that's how these integrals are set up, and that's it. And your book, of course, uses TU and TV here instead of RU and RV, just to indicate, again, to reinforce the idea that these are tangent vectors. RU, DU, and RV, DV are infinitesimal tangent vectors whose cross product gives you the magnitude of whose cross product gives you the area. Okay, now let's move on to how this might apply to the big integral theorem, Stokes theorem, and divergence theorem. Normal vector times your delta SI. Now again, I was using delta SI in a general explanation, but we're going to make this delta Sij because of course we've got an IJ here. Okay, your N delta Sij, which is the same as the N delta Si here, but that should be. I swear I just saw an Si without a J, but there's the J. Okay. So again, we're just doing this. Okay, so we do this. We're going to need the N delta Sij. Why? Because that gives you, well, that's just the cross product of the RU delta U and RV delta V vectors. These vectors, which again, gives you the area of the parallelogram defined by those vectors. That parallelogram, repeating for the 12th time, being the image of this parallelogram in two-dimensional parameter space on this three-dimensional column. Okay, So we have the normal vector times the area here. And the flux of the vector field F is just F dotted with that normal vector, okay? Normal vector, again, has direction perpendicular to the surface and a magnitude which is equal to the area of the surface. Okay, I think we got another word. Okay, well, here we just go ahead and execute the RU cross RV. Doesn't mean we kill it, it means we go through the steps. Okay. I've got RU here and RV here. Okay. You can do the cross product. Well, there is the cross product. No, I didn't do the cross product. Okay, here's the cross product. I did the cross product using the distributive law, and there's some kind of an error in it, but just quickly, I use a distributive. You write it out as a determinant, ijk, and then negative v sine u, v cosine u, 0, and then cosine u, sine u, 2 for your third row, and you do the determinant, and you get the cross product without ever understanding that it comes from the distributive law. I find the distributive law generally more convenient if one of your vectors, at least one of your vectors, has no more than 2 non-zero components. And I didn't want to write out the determinant, have a lot of space and time. So I took a lot of space and time trying to figure out why this didn't come out the way I thought it should. But let's go over it again. Okay. This is an I vector. There's a vector in the direction of the I vector. This crossed with this is 0 because I cross I is 0. This crossed with this is, well, it's going to be your negative v sine u times your sine u times I cross j. I cross j is k. So we get a negative v sine squared u k. Negative v sine u, the sine u gets negative v sine squared. And then I cross k, well, here's I, here's k, it's negative j. Okay. So we do the j component crossed with the k component. V cosine u times 2 is 2v cosine u. And then we're not doing the j yet. And so we're doing the I component, k component. So we're doing the v sine, negative v sine u times 2, which is negative v sine u. I cross k is 2, so there's a negative 2 v sine u j. Okay, that's got to be right. Okay, then v cosine u j crossed with cosine u I, j cross I is negative k. V cosine u times cosine u is v cosine squared u, so there's a negative v cosine squared u times k. And here's where I'm upset. I think the sign of this should match the sign of this. Let's make sure that I've done this right. I did it 3 or 4 times. I convinced myself, but you know, I don't know about my own sleep. But this is going to be a j cross a k. Well, j cross k is positive I. This is positive and this is positive. So why darn it comes out positive. You get this, where this came out negative. Now that doesn't make a lot of sense in terms of the picture. If this thing is above the first quadrant of the xy plane, the vector is going to be down and in the positive j and positive, or the positive y and positive x direction. So we should have a positive multiple of j and a positive multiple of k and a negative multiple, positive multiple of j, positive multiple of I, and a negative multiple of k. Now we have all that, except we don't have a negative multiple of I. We're in the first quadrant, above the first quadrant, so the sine and the cosine are both positive. So this isn't matching, and I still don't know why. Yeah, worry about it and work it out. At least go with the mechanics. Something's wrong. We're going to go ahead with the mechanics and hope to eventually someday discover our silly error here. Okay, hopefully you can see everything that's pointing to performance. Make sure. So RU cross RV has a magnitude equal to what? Well, you just add the sums of the squares of the components. Well, before you do that, you simplify this. We've got a couple of k's in here. So we factor them out. We get a negative v factors out. And then we have a sine squared u plus cosine squared u, which is just 1. And then that's times k. So we get negative vk. And that sine squared plus cosine squared thing, something you always got. It comes up all the time. Okay, then I kind of unwisely factored out a 2v here. And then I have times a cosine ui minus a sine uj. And much as I hate it, I have opposite signs here. I can understand. I didn't want to be wrong. Okay, I really should have kept that distributed. So I'm going to actually do that. I'm going to call it 2v cosine ui minus 2v sine uj. Because now I can see what my k, I, and j components are. V, negative v squared is v squared. 2v cosine u gets squared, and the 2v sine u gets squared. And then you use the Pythagorean identity and all that stuff. You add up the square root of 5 times t. That actually makes a lot of sense because the slope of this thing is 2. And I heard somewhere, again. Okay, I've kind of drawn a triangle on this. I started to draw above the line that I brought below. So this would be V, this would be 2V. But you can check out the Pythagorean theorem says that the Pythagorean theorem, if I pronounce it correctly, says this is square root of 5. So this thing has twice square root of 5 times the length of this. So an area increment is going to have square root of 5 times the area, something I don't want to specify right now. You can think about why this kind of confirms the square root of 5. Okay, well then your total surface area, we just integrate the magnitude of RU cross RV. Okay, as we say here, we end up in this case with a very simple integral, which is 9 squared 5 times pi. Okay, then I always like to check things. I don't know if you can see this. This over a little, probably smudge a bunch of stuff. If you take this cone and slice it, let's say down here, at any point on this circle up at the top down to the origin, if you slice it there and fold it out, you get an arc or a sector of a circle whose radius is equal to this distance, which is square root of 3 squared plus 6 squared. Of course, that's just this order 3 times square root of 5. Okay, so if you have a circle of radius 3 square root of 5, its total area is the square of that, which would be 9 times 5, which would be 45 times pi. Pi r squared, 45 pi. Okay, 45 pi is bigger than 9 square root of 5 pi. And you can test that. So this is only some fraction of the total area of your surface. And you should understand There's a formula for the area of the sides of the cone. But you don't really need that formula. If you just slice it and figure out what this angle is here, you know what portion of a circle this is. That's why I'm not going to go any further with that. You really make yourself a note out of it too, because it helps check things. And it's important in its own right. Okay, well, now, we go to a vector field, f of x, y, z, and I alluded to that over here. Okay, now it's an f of x, y, z, which is going to be a little f, a little g, and a little h, multiplied by I, j, and k, respectively. And each of these is a function of x, y, z. But then ultimately, each is a function of u and v, because x, y, and z are functions of u and v. You don't see it all, but right there's a parameterization. Okay, I guess I can move this over, where we can once again see the parameterization. Okay, so instead of x of uv, we would just substitute f of v cosine u, v sine u, and 2v, these functions. That would give us our x, y, and z, give us this. But of course, by the chain rule, we can take derivatives with respect to u and with respect to v, if we need to. So, well, that equals what? Well, that equals an et cetera, but now let's go ahead and get a good function f. And then we're going to integrate f dot n with respect to circle check. Okay, we're going to do, well, I never did write it, except implicitly here. Now, for the moment, we're going to let f be the gradient of some scalar field. Okay, and the scalar field, some scalar function. Scalar function, I just chose x squared y z cubed, three different powers of x, y, and z multiplied together. Then we do the gradient of that. The gradient is very straightforward. X derivative is 2xyz cubed. That's times your I vector. Y derivative is just x squared z cubed, just times your j vector. And the z derivative is 3z squared times x squared y, 3x squared y z squared. That's times your k vector, and I'm not going to review the gradient vector. It's just partial with respect times I, that's partial with respect times j, partial with respect to y times j, et cetera, et cetera. Okay. Now, on our surface, then, we can just directly substitute the expressions for x, y, and z into these expressions, 2xyz cubed. If I did it correctly, gives you 16v to the fifth cosine u sine u. That's times I. X squared z squared gives you this times j. X squared y z squared gives you this times k. Then the flux through the surface is the integral over the surface of f dot n ds. There it is from one increment. Right here it is. If you sum up all the increments and approach 0, which is where this would go. Okay, so we're actually integrating the, but we're summing up this expression. But now we have something that maybe makes a little more sense instead of these more abstract symbols for the I, j, and k components of f. We have the I, j, and k components as expressed in terms of the parameters that define the surface, parametric representation of the surface. So on the surface, there's your function f. Well, then f dot n ds is what? Well, here's your f dot your normal vector, which we got previously. Okay, by so forth. The plus here and a minus here that I just don't like. I still think it's wrong, but I can't find it. Okay, well, we do the dot product, and that comes out very easily. The k with the k is going to give us this with an extra b, which will give us b to the 6 cosine squared. Maybe I didn't do that one first. There it is. Throw do the k dotted with this k. Well, it's going over here, here, and here dotted with these. The I component dotted with the I component. I've got these out of order, which wasn't a good idea if I did it. The I component dotted with the I component just gives you this expression times this expression. You got a b to the 5th, b gives you b to the 6th. You got a cosine u, cosine u gives you cosine squared u. You got 16 times 2, which is 32. And you got a sine u, which I didn't write down. Well, there it is. And then your j component times your j component. Again, you're going to get a b to the 6th. Cosine and cosine squared will give you a cosine cube. This is not the j. This is the j. Okay, again. Should have had these in order, so I don't do that sort of thing. This times this. Okay. You're going to get a sine u and an extra b and a multiple of 2. That's going to give you a multiple of 2 is going to give you a 16, and it's a negative 2, so it's a negative 16. And the b's give you a b to the 6. The sine u gives you a sine u, cosine squared u gives you cosine squared u. Okay. Yeah. So it's come up. Then the k component times the k component, you're just going to add a b onto this and make it negative. So you get a negative 12b to the 6, and then your cosine squared u and your sine. There it is. Now that's something you can integrate. Okay. The worst thing you got to do is integrate the cosine squared. So you got a formula that relates the squared cosine to the cosine of 2 theta. And you got to use that identity, and everything else is very straightforward. To integrate this with respect to u, going to let u equal cosine. We're going to let u. You use a substitution. Substitute your variable, call it w for cosine of u, and you're going to get a w squared, and then the dw is the differential of the cosine, which is the sine times your dw and so forth. And it's just basic substitution, which you ought to be very familiar with. And if you aren't, you ought to do about 100 of them. Okay, so there we have it. It's an easy integral. I think it's still going to be long. Okay, square the I and the j components here should have the same sign. It just geometrically has to be, but it doesn't seem to be. Okay, one last little note. We note that because f is a gradient, it's conservative. So its integral in any closed curve has to be 0. Of course, the integral depends only on your starting point and your end point, and the values you get at the starting point and end point are equal, and you're subtracting them. Okay, by the fundamental theorem of vector field. So here's our cone. Let's let C be the circle up the top of the cone. Then the integral of f ds, f dot ds has to be 0, because this is a closed curve and f is a conservative field. Okay. And Zoom is hesitating a lot. This needs to be. I think we can finish up. It follows by Divergence theorem. I'm sorry, by Stokes theorem. Sorry, I didn't curl. That Stokes theorem says the integral around the curve that bounds your cone or your surface, whatever it is equal to the integral over the surface of the curl of that function with respect to s. So we know that this integral is 0. We could do the curl of f. We do del cross f, okay? And then we could integrate that with respect to s. It would just be the same as the area in the area integral. So I don't say integral. And we'd have to insert the cross product here into this integral, and we would have to get 0. Not sure we would because of that sign thing that keeps bothering me, but that's what it would be if everything was done correctly. Not only that, but the same is going to be true for any surface that's bounded by this circle. So if I had a paraboloid bounded by this circle, all I have to do is do the integral is still going to, the integral of the curl is still going to be 0, no matter what the surface is. It's bounded by this circle, hemisphere, a paraboloid, whatever. If it's open up there at the top or the bottom, wherever that circle is, the integral of the curl is going to be 0. Since this is true for any surface at all and its boundary, for any conservative field F, then turns out that the curl of your conservative field always has to be 0. Now, it's really easy to prove that if you just write out in symbols what the divergence of the curl mean, or the gradient of the curl mean for a function. But this is kind of a neat correlation with Stokes theorem, which is, of course, why we're doing all this. Because Stokes theorem and the divergence theorem, Stokes theorem, as we see by this example, involves a line integral or a surface center. Line integral has to be for the surface. Divergence theorem means that the integral of the divergence through a volume, so you got to do a volume integral, is equal to the flux through the surface. So you have to do a surface integral. Now, the thing about Stokes theorem and divergence theorem is sometimes it's really hard to do one of the two integrals that are involved with the theorem. Okay, so sometimes for the Stokes theorem, sometimes the integral around the curve is much easier to do than the integral of the curl on the surface, or vice versa. Sometimes the integral of the curl on the surface is easy, but the line integral is next to impossible, maybe impossible. Doesn't matter. You know what the line integral is if you know what the surface integral is. And similarly with the divergence theorem. Okay. If you know the volume integral, then you know the flux integral through the closed surface. If you know the flux integral through the closed surface, you know what the total divergence is. Okay. Well, this is a lot of the mechanics that's involved with the Stokes theorem and divergence theorem. And they're all related to Green's theorem in a way that's pretty clear if you just really look at it. And that's what we need to tie up here at the end of the course.